So yeah, this time I'm going to be talking about Introduction to Natural Language Processing. So this is just a start out, kind of, organizing information about natural language processing, some of the things we need, defining. Also going a little bit through classes here on natural language processing. One characteristic of this class is it's trying to build up your skills so you can go in and do a project at the end where the project is project. Okay, can you hear me? Let me check my audio.
I can hear now. You're good now.
Okay, sounds good. So anyway, this always happens. Sorry about that. So what is NLP anyway? It's basically technology to handle language. It usually refers to text, but it can also refer to other things as well, like natural language through speech. Using computers, human language. And so does anybody know what the difference between a natural language and an unnatural language is? Or anybody know a good example of an unnatural language? C++, yeah, good example. What about another one? Yeah. How are we defining language? Oh, that's a much harder question. Usually it's a sequence, or I'm thinking of this off the top of my head based on my knowledge. So if I get it a little bit wrong, I apologize. But basically, it's a sequence and combination of symbols meant to convey some variety of information. Any other example of an unnatural language? C++, Python, Java, those are all good examples. Math, yeah, sure. Yeah, kind of. I'd say that's more of a code than a language because it's a way to express, English or anything. It's a character set, yeah. Some other examples would be things like Esperanto or Lajban, which are like languages that are created to communicate between humans, but they were created by humans as kind of ideal languages, yet they're not so ideal because nobody understands them, so you can't actually use them. But anyway, so NLP is handling human language or natural language, usually computers. It can be used to do several different things. I tried to organize them into three major categories. The first one is aiding human-human communication in some way. So this could be doing things like machine translation, translating between languages. Is aiding human-machine communications. So taking a natural language, having it communicate with computers to get information from them or make them do something or something like that, including questioning and dialogue. Another thing is analyzing and understanding language. So this could be things like syntactic analysis, text classification, and relation, entity or relation recognition and linking. So these are taking in language, turning it into some sort of structured format to extract information from it in an easily usable way. And almost all of us probably use NLP several times a day, maybe without even noticing that we're using it. I love talking to my Google Assistant and asking it questions at the dinner table when I don't know something. Most people I talk to at CMU think I'm very weird for like actually liking to do this, but I find that fascinating. You can also use it to translate. If I find content in other languages, I use that too. And everybody uses it in different ways. You also might implicitly be using it by using your favorite social network, where your social network is analyzing all of the posts and recommending new ones to you based on your content preferences. So there you're using it, you're not using it yourself, but other people are using it for you. Here are just some examples. NLP can answer questions. Oops. Okay, so people can hear me now, that's good. So NLP can answer our questions. So for example, in Google, I put, where was the first movie theater in the US? And in big bold letters, it gave the correct answer of Pittsburgh. And indeed, if you want to go see the first movie theater in the US, you can go downtown and search for it. There's actually a walk around downtown this weekend, apparently. So if you want to go to that, I'm sure you can see the movie theater as well. NLP can also translate text. So one of my favorite things to do every time I do this course is to grab the first sentence or the first paragraph from a Japanese newspaper and put it into Google Translate. Because it gets a little bit better every time. And this is pretty good. So this was completely, I just grabbed the sentence, the first paragraph, and as far as I could tell, it's basically right. I didn't notice any problems. I'm fluent in Japanese, yeah, so I can actually tell that it's working, yeah. NLP can also do other things like scientific inquiry. So like, let's say you have a question about the world and you want to answer it by examining lots of language, NLP to do this. And I have an example from computational social science, which is answering questions about society and observation. And an example question is, do movie strips portray male or characters with more power or agency? And this tells you a little bit about a culture, for example, like if, people from the same of different genders are portrayed in similar ways, then that's a relatively gender equal society. But if they're portrayed differently, then it's maybe not as much. This is a paper by Martin Sapp from a long time ago, but he's now a faculty member here, of course. So basically, in order to do this, what they needed to do was they needed to have a dictionary of power and agency terms, like what verbs indicated power and agency, but they also needed to do a syntactic or semantic analysis to identify who was the subject and object, or the agent and patient of those verbs. And so in order to answer this question, they had to have good, well-working natural language processing technology. And using this, they were able to say something like men were more often portrayed with agency or power in the movie scripts, which indicates, societal biases, for example. On the other hand, NLP fails at answering some of our questions. So this is just an example of another question I asked: who won the 2021 Pittsburgh mayor Democratic primary? And here it said 2021 Pittsburgh mayoral, 2021 Democratic. So it gave me some highlighted terms that don't actually answer my question. However, if you look on Wikipedia at the time that I did this query, there was a sentence at the very beginning of Wikipedia that actually tells you the answer. So basically, Bill Peduto, Democratic Mayor Bill Peduto, ran for re-election to a third term in office, but lost renomination to State Representative Ed Gainey. So this tells you that Ed Gainey was the winner. It doesn't tell you directly, but a human would be able to infer this. So this indicates kind of a mistake in language understanding, or an incompleteness in language understanding. This is another one of my favorite examples. Who invented neural machine translation? And Google decided to tell me who invented neural machine in French. So where do you think this failed? Where do you think this this search box failed for me here?
Intent resolution.
Yeah, I heard machine translation, understanding, and intent resolution. I would say I don't know French well enough to be 100% certain in this, but the translation actually looks pretty okay. I think the problem is that it's the intent resolution. Basically, Google decided that I wanted a translation when actually I wanted an answer to my question about this. Also, it didn't answer the question below the translation box. Yeah.
I'm wondering with the intent resolution, like that's what we take into account, like European resources, like translating
Yeah, so that's a really good question. One way you could figure that out is by putting in a search box yourself in like an anonymous window or something. Maybe it will detect you're sitting in an like CMU machine, like natural language processing class, and figure out that you want translation. But you get a Wikipedia article. Does it give you the answer? Oh, very, very good. That's actually correct. So, yeah, okay. So maybe it works sometimes, and it's based on history. Yeah.
Yeah. So that if you add the word answer to your query, then afterwards.
Okay. Yeah. So if you add it to the query, it actually works. But there are similar failures like this. It doesn't fail all the time, obviously, and Google is very good. So. Here's another example. It gets harder and harder to come up with machine translation examples that don't work. So every time I kind of have to find a language that's sufficiently difficult. This is Kurdish, and I put in just an article from Voice of America, translated it on Google. It's actually reasonably good. However, three researchers led by independent fossil scientist Gregory Paul of Baltimore, Maryland, argued in March 2022 that T-Rex should be recognized as 3 species. However, it does make a few mistakes. Number one, it calls a paleontologist a fossil scientist, which is not bad, but it's not what I would write in English. It's not how I would translate it. Another thing is T-Rex, which means king of ferocious lizards, T imperator, which means emperor of the savage lizard, and T Regina, which means queen of the ferocious snail, which is maybe also not how I would have translated it, but you know, hey, it's pretty decent. That being said, it also completely falls apart on like social media text or other things like that. I ran my my wife's social media text through, or my wife's like email to me through Google Translate yesterday, and it was completely wrong. So it's not necessarily the case that Japanese works and Kurdish doesn't. It's also, you know, shades of gray depending on what type of text it is. NLP also feels, even for basic tasks that we think very good. So these are two examples from Spacey and Stanford Core NLP, which are kind of gold standard, you know, very nice methods for doing entity recognition. And I just threw in a random sentence from the New York Times, and Stanford Core NLP recognized Baton Rouge as an organization, and also Hurricane Ida is an organization here, or Ida. So you can see that even just a random text from the New York Times, there's one failure out of this. So what I want to do in this class is ask, why do current state-of-the-art NLP systems work uncannily well sometimes? So why are they so good? Why do current state-of-the-art NLP systems still fail, sometimes in very inexplicable ways? And how can we create systems for various tasks, identify their strengths and weaknesses, make improvements, achieve whatever we want to do with NLP. So this is a tall order, but it gets easier and easier every year. Techniques get better and better. So that also allows us to tackle more and more challenging problems every year. And just to give one example, just 4 or 5 years ago, we started working on a word problem solving data set called RACE, which was basically English quizzes for Chinese students. And when I first started tackling it, I looked at this and I'm like, I have no idea how we're going to ever be able to solve these problems. You know, like these look really hard. They require complex reasoning and other things like this. And now we have systems that do, you know, like 80 to 90% accuracy on these data sets. So it's really pretty impressive, the progress we're making. Okay, any questions before I go on to the basics of NLP system building? Okay, great. So I'd like to talk about a general framework for NLP systems, and just about any system you're going to work with or make in this class is more or less follows this framework in some way. And basically what we do is we create a function to map an input X into an output Y. And here are some examples of doing this. So input X, we have text and text in another language, and the task here might be translation. We might have text in a response where the task is dialogue, text in a label, text classification, text in linguistic structure, like dependency structure or something like this. This is language analysis. And to create a system, we basically can use a few different techniques. The first thing that we could do, and in fact, you still might be the first thing you want to do if you're working in the industry or something else like this, is manual creation of rules to solve your problem for you. Another way you can do it is machine learning from paired data. So you get input and output examples, and you train a model to solve from this. When creating a system, we use 3 sets of data. If you've taken a machine learning course, this should come as no surprise, but basically training set, which is generally a larger data set used during system design, creation, and learning of parameters. We also have a development set, which is called the dev or validation set pretty frequently as well. This is a smaller data set for testing different design decisions or hyperparameters. And a test set, which is reflecting the final test scenario. We try to avoid using this to make design decisions. So just to give an example, a lot of NLP courses, you kind of skip this step and jump directly into creating a machine learning based system. But I'm a pretty strong believer in like looking at data and understanding what's going on with data first, so you can make the appropriate decisions even when you finally use machine learning in the end. And I think this might be a good exercise to do in order to figure that out. So for the task that we're going to try to handle, we are going to do review sentiment analysis. So given a review on a reviewing website, decide whether it is a positive review, a negative review, or a neutral review. Just to give a quick quiz, does anybody know the difference between sentiment analysis and emotion analysis? Any brave people who want to take a guess? Yes. Mm-hmm. So that's a really good point. So just to repeat for the people on Zoom, emotion is more multifaceted. Like there's different dimensions of emotion. So that's one important difference. It actually wasn't the one that I was thinking about though. Any other ideas? Yeah.
I think sentiment analysis is about how intensely sentiment is towards a positive or negative side. Mm-hmm. That's like happy or angry kind of thing. Mm-hmm. It's not like intensity. And whereas on the emotion side, it's not like fear or anger or mm-hmm.
Yeah.
Whatnot. There are different tones which might be different.
Yeah, it's more like so sentiment is more about intensity, emotion is more multifaceted. It is true that emotion is more multifaceted, but that's actually not what I was thinking about. Yeah, so sentiment's more to do with a statement of a feeling, and emotion is more about how somebody's actually feeling. Kind of, yes. These are all very good points. And in fact, the multifaceted thing was not what I was thinking about, but it's completely correct. Sentiments, oh, and on Zoom, actually, I have the correct answer, which is sentiments have a target. So a sentiment is expressing an emotion, expressing an opinion about something. So when we're talking about review sentiment analysis, it's a review of a particular thing. So that's the main difference, but there's also the multifaceted aspect and whether you're actually expressing it or not. So these are all good points too. So anyway, sentiment, we have like, I hate this movie, I love this movie, I saw this movie. I hate this movie would be negative, I love this movie would be positive, and I saw this movie would be neutral. And so we have this code repository here that you can take a look at if you want. And we can look at the data. So let me just open up. As I said, we should start out by looking at the data. And so I will open data SSD sentiment text free class. And we look at the training set. And what this data looks like, is something like The Rock is destined to be the 21st century's new Conan, and that he's going to make a splash even greater than Arnold Schwarzenegger, Jean-Claude Van Damme, or Steven Seagal. So it's a little bit more complicated than I love this movie and I hate this movie, obviously. So that's what makes this, task kind of interesting and challenging. But this is very positive, obviously. If we go to neutral, you'd think by now America would have had enough of plucky British eccentrics with hearts of gold. So this is like maybe vaguely negative, but I guess neutral. And then if we go to positive, go to negative, this isn't a new idea, or a sour little movie at its core, an exploration of the emptiness that underlay the relentless gaiety of the 1920s. The film's ending has a what was it all for? So, people get kind of flowery with their language in these reviews. So anyway, now that we've taken a quick look at the data, which I recommend you always do when you start working on a new task, I'd like to introduce a three-step process for making predictions. And basically this three-step process, the way it works, you start out with feature extraction. And what this does is this extracts the salient features for making a decision from text. From this, we do score calculation. So this calculates a score from one or more possibilities in the decision function. So choose one of the several possibilities based on the scores that we calculate. I have another quick question, which is in feature extraction, and especially if anybody's taken an information theory class or something like this, we can think back to it. So in feature extraction, what are we doing? Are we adding more information to the text that we input? Yes or no? No. I see a lot of people shaking their heads no. And why is that? Yeah. Right. Yeah, we're taking existing information and manipulating it to a useful format. And information theory tells us that you can never take in something, run it through a function or a deterministic function especially, and add additional information to it. Any manipulations either keep information constant or remove information. So basically, if we think about feature extraction, what this is doing is this is taking a very complicated, unstructured, with lots of information and removing all of the information we don't need to solve the task. And this is actually important into neural networks and stuff.
It's a small nuance, but if you're using some sort of any tool which has some existing context to do feature extraction, we adding some
oh. Mm-hmm.
And it has been trained on some context.
Mm-hmm.
Find out so it's using some existing information that it has to find out what it thinks now. So it might definitely miss some entities out, but it will take some entities which may not be so. So would that be injecting existing information into it?
Yeah, so that's a really good example. So like, let's say we take Spacey and do named entity recognition. Is that adding information? From an information theoretic perspective, it's not adding information because Spacey is a deterministic function that will return the same result every time. So sure, Spacey, has access to a bunch of external resources and stuff like this, but actually, what it is doing by doing entities extraction is it's taking the original text that you had and it's extracting the salient information so that your classifier, for example, can focus on the information that's important and not focus on the other information that isn't important.
What if
Yeah.
we try to get contextual memories from a sentence and the sentence never had any of the context that the model was created? That be a way of adding information which doesn't exist or reading between lines, so to speak, but the lines don't exist later?
Yeah, so that is not adding information that didn't exist in the original text. What it is doing is it is converting the information that existed in the original text in an easier to access format for a downstream classifier, essentially. And actually, if you're interested in this, there's a nice concept of V information. V, like the letter V. I searched for it and I'm getting information about BTS. So I can't find the paper immediately, but let me take a note that I need to share the paper. So yeah, there's a nice explanation of this. I won't go into it too much in the class because it's a kind of important, kind of complicated topic, but I'll follow it. And so basically what you need to know is feature extraction is the information that's not useful for your downstream class. Yeah.
Going forward on this,
yeah.
From an mission theory perspective, knowledge injecting information, but for large language models, break down to like large structures to make creative and large structures to get data, especially if we're doing control language generation. We are effectively getting that information about what, like it will hallucinate and it will in controllability, we will tell that okay, you don't want to do this or you don't want to do that. Isn't that like where's the fine line between injecting information versus?
Yeah. So basically, I'm happy to talk about this more in detail later, but the fine line is basically if you do any deterministic transformation of an input into an output, you're never adding information, you're just transforming from one to the other. And the reason why, if you're familiar with information theory, is because basically, let's say you have an input X, the amount of information in the input X is essentially the number of bits that you would need to express the input X would be log P of X here, log 2 P of X, according to coding theory or arithmetic coding or other things like this. And if you add something, some other output where the probability of the output is 1, in other words, it's a deterministic output, then the probability of both is this, and this is 1, so this becomes 0. So you're not adding any more bits of information to them. But yeah, yeah. Sorry, I mentioned this as kind of a trivia question, but it was I didn't mean to go this long into it. But the important implication of this is that feature extraction is basically it's getting the most important information out of the inputs. It's not necessarily like adding new information to it. So it's, if anything, it's removing the information that's not useful for your downstream class. Okay. So formally, we'll define a few functions. We'll have H, which is our features that we extract from our input X. We have our score calculation. Usually our score calculation takes this form. So we have a linear function where we multiply weights over each feature by the features that we extract and get a single scalar score. So this is a dot product here. For multi-class classification, we have this this S vector here where we have a score for each class we're trying to classify. So if we were just trying to do positive and negative sentiment, we could multiply a weight vector and get a score where if the score is positive, it's positive sentiment. If it's negative sentiment. But if we have 3 sentiments, we would get a score for positive, neutral, and negative, and the higher score. So then we have a decision rule, and this is maybe not covered as broadly in many like machine learning or natural language processes, but the decision rule basically says, given the scores that we have, let's output let's output the correct answer. And usually this is for like multi-class classification, this is just taking the max. But if you're doing something like machine translation or parsing or something like that, that's a little bit more structured, then it becomes more complicated and we need things like beam search or other things like this, which I'll cover in a later class. So another reason why I do a rule-based classifier first is it allows us to do all of these steps in a very simple way. So I have the code here for rule-based classifier for sentiment analysis. It covers featurization, scoring, the decision calculation for analysis to tell you where you're going wrong.
There's a question in the chat.
Yep. Is my understanding correct? Yes, basically that understanding is correct.
Well, it does kind of like also like determine what you focus on.
Yeah, it determines what you focus on, stuff that you don't want to focus on, but also feature that it has is it like might it make it possible better a linear classifier here. Okay, so let me pull out this this Jupyter notebook that we have. And there won't be a whole lot of code walks in this class, but this is one of the ones that we will be doing. And so basically, this is a notebook where we're attempting to build a rule-based sentiment classifier. It takes in a text X and returns a label of a label of 1 if it's positive, -1 if it's negative, and 0 if it's neutral. It's trained on the Stanford Sentiment Tree Bank, which is the most famous sentiment analysis tree bank. What we're doing here is we're features given an input X. So we have our features here. The way we do this is we first split X on white space. This is a very common thing to do in English, but it's also something we can't necessarily take for granted. So for example, if it was Chinese that was not written with any white space, then splitting on white space would do nothing and we'd have no way to get words out of here. So just to won't work all the time. And then we have good words and bad words. And the good words are words that indicate positive sentiment. Bad words are words that indicate negative sentiment. And then we extract 2 features. The first feature is word count. So that's the number. That's the number of we get something. Get one of the good words in our input. Bad word count is the number of times we get a bad word. We then have a bias, and the bias value is it allows us to assign a default score to the text. And then we have feature weights. So this is our W here. And we have our H here. So the H is the feature vector, and then the W is the weights. And so what we end up doing is, like, let's say this is a good movie. We might, our first feature, good word count, has a value of 1. Bad word count has a value of 0. Bias has a value of 1 because the bias always has a value of 1. And then we multiply this together with the weights. So the weight here is 1, the weight here is -1, and then the weight for the bias is 0.5. And then based on this, if we take the dot product, score. So this is how we extract the features. Oh, sorry. So this is the feature extraction just returns the features. We also define the feature weights. Then we read in the data. So we have 1, -1, and 0. One thing I should note here is actually, sorry, this is a little bit confusing, but I'm just attempting to predict. Oh no, sorry, no, never mind. I'll get back to that. Okay, so so we have our inputs here. Now, the second thing that we need to do is we need to have a decision rule. So basically here, what we're doing, this is just taking the dot product here. So this is calculating the score. And then this here is our decision rule, where our decision rule says if the score is greater than 0, we return 1. If the score is less than 0, we return -1. Otherwise, we return 0. So this is our decision rule. We could also have something where if this was greater than equal to 1, we'd return 1. That would also be an option. We also have evaluation code. So you'll always need evaluation code to evaluate your outputs. For text classification, it's relatively simple. We use like accuracy, or we might use another method called F-measure that I'll talk about later. For evaluating machine translation or dialogue or other varieties of text generation, I would almost argue that evaluation is as hard as building the system itself. Like you get outputs and it's very, very hard to tell whether they're actually good or not. But anyway, here we're just calculating accuracy. So we calculate the prediction according to the classifier. We calculate our denominator by adding 1 to the denominator. And if the prediction is correct, we add 1. So then we calculate our training accuracy and test accuracy. Our training accuracy is 43. Our test accuracy is 42-ish. And then another thing that I really encourage you to do, it's actually this easy, is to actually look at the outputs where your system is failing and see what's going wrong systems, so you can understand why you're. I've given you. Okay. Hi everyone on Zoom. I'm sorry, my internet died, so that's why I disappeared for a while. Apologies. Okay. Going back to where I was. Okay. Back to where I was. So. Okay, there we go. So here's our error analysis. And basically what I did here was I just randomly selected examples where the model got it wrong. So we have the innate theatrics that provided its thrills and extreme emotions lose their luster when flattened on screen. So you can see that this is pretty obviously negative, but the model here predicted it as positive. So while we were waiting over the for the Zoom to recover, or for the internet to recover on my computer, one mention was, what if we set the bias weight differently and we instead set it to 0, which would mean that by default we would return neutral. Seems like a pretty good idea. We return neutral when we don't have any positive words or negative words. Let's see how that works. Not a great idea. Yeah. Is it better to change the bias? We could also change, you're right, we could change the threshold in the decision rule. So that would be another way that we could solve this problem. Is there a preference on what's better? I think they're actually, in a normal model, they're actually pretty similar. Like the bias is kind of a threshold for which one you pick. Yeah, in this case, I'm doing a slightly unusual decision rule. I'm actually doing this decision rule on purpose because it's like just to demonstrate that there's different options for decision rules. But yeah, in most cases, they are mathematically equivalent. So any other ideas? What can we do to improve our classifier here without downloading BERT? Yeah, so can we get some more good words and bad words? Any ideas? Nice. Great. Enjoy. Enjoy is actually very good. Maybe you want enjoyed too. What about here? Terrible, disappointing. So
I think side might be problematic because it's side will be.
okay. Any other ideas? Lost?
Lost interest.
Oh, lost interest. Okay, that's an interesting one. Angry. Okay. Okay, so let's stick with these ones and see how far we get. Oh, I should change our bias back to 0.5 maybe. Yeah, good job, everyone. You've increased accuracy by 0.3%. Congratulations.
That's enough for a paper.
Yeah, it's enough for a paper, and I just need to come up with a nice acronym, and we're all set. Yeah, so basically, like what you could see here, we were working entirely off of intuition and other things like this. Maybe not the best way to do this. I actually have a secret, which is if you train a model, one of the lowest sentiment words is Seagal, like Steven Seagal, the action figure. And I don't think anybody would have thought of that in here without like looking at the data, right? So, this demonstrates the difficulty of creating a rule-based system, even if we're just looking at vocabulary. Word stemming, yeah, we could do stemming. I probably could do that if I had 5 to 10 minutes, but I'm not going to spend 5 to 10 minutes implementing the Porter stemmer. So anyway, regardless of the type of system you're making, one effective recipe to improve your system is looking at what's going wrong with your system, modifying the model in some way, measuring accuracy improvements, accepting or rejecting the change, and repeating from one. And finally, when you're satisfied with the train or dev accuracy, you evaluate on test. Yeah.
Yeah, question. So I don't think you have an explanation of why setting that bias weight to be 0 actually worsened the change.
Oh, why did we set the bias weight? Why did setting the bias weight to be 0 worsen the accuracy? So that's a really good question. Let me see if I can very quickly find the answer for you. So balance of the data type itself. Yeah, so let's do this. Label equals, oops, for y and y test. If y not in label test, y equals 0, label test y is equal to so basically what we can see is that neutral is by far the least common tag in the test set. And because of that, doing that by default seems like a kind of bad idea, right? And We could even do this. Yeah, so basically that's the reason why. I saw another hand. Yeah. Yeah, so that's a really, really good point. Just to repeat it for everyone. Step 2 says modify the model. I should have actually said modify the system, because like a system, like an NLP system is very often a model. The training for a machine learning based system, it's the model, the training data that goes into the model, and the optimization algorithm. And all of those are important things that determine the accuracy of the system. So yeah, it should have said system.
Right, but what if you look at a sentence and just take everything after the word talk?
Yeah, that's a good question. Why don't you do that and report on Piazza or something? Not too hard to do in the Jupyter notebooks available. Cool. So there are some difficult cases. Some example cases are low frequency words. So for example, we have tenuous and purport. These never appear in the test set even. Sorry, never appear in the training set, but appear in the test set. So there's no way you could get these by looking at the training set. There's no way you could easily get them by just looking at the supervised training data. And similar here. So one solution would be to keep working until you get all of them, or incorporate external resources such as sentiment dictionaries. Another thing would be conjugation. And so, for example, entertainingly, magnificently, that goes into the stemmer like comment on Zoom, for example. So we might want to stem these into their base forms. However, this would require a stemmer or some sort of analysis, and we don't necessarily have that for Kurdish, for example, if we wanted to build a Kurdish sentiment classifier, right? Negation, this is the favorite. This one is not nearly as dreadful as expected. I don't know if that's positive, maybe neutral. Serving Sarah doesn't serve up a whole lot of laughs. So if you look at a whole lot of laughs, that looks pretty good. But if you look at doesn't, then not. If a negation modifies a word, disregard it. You'd probably need to do some sort of syntactic analysis or something. What about metaphors or analogies? Puts a human face on a land most Westerners are unfamiliar with. Positive. Green might want to hang on to that ski mask, as robbery may be the only way to pay for his next project. It's negative. Has all the depth of a wading pool. Pretty negative, right? Yeah. I don't know how to answer this, and actually one of my students and one of the TAs for the class, Emmy, has a paper on metaphorical understanding, and even quite large language models are not super great at doing this either. So I honestly don't know the answer to getting these right consistently. Also, of course, other languages. If there's any people here who know Japanese, you might be able to do this, but if you don't, then you might have trouble, right? Solution, learn Japanese. Okay, so machine learning based NLP is what we're going to spend most of the rest of the class on. And here, we essentially have a learning algorithm, a learned feature extractor, and a scoring function. And then we have an inference algorithm that gives us the outputs. One example of this is a bag of words model. And basically what this does is this extracts every single word in the input as one of our features, but then it automatically learns the scores for the outputs for the scoring function. And that gives us a score. And the features F are based on word identity, the weights are learned. If you think what problems mentioned before would this solve, let's say you had really large training data. This might solve the rare word problem, for example. It also might solve the conjugation problem somewhat, because you'll see lots of conjugated words in your training data. But it wouldn't necessarily solve the negation problem or other things like that. A better attempt is neural network models. And basically what they do is, they featurize each word that you're dealing with, run some complicated function to extract features, and then multiply these by weights and output a score. And This function can be arbitrarily complicated, and in fact, neural networks can learn arbitrarily complicated functions. It's a well-known fact about them. And so because of this, theoretically, neural networks should be able to solve NLP. You know, they do very well at some things, do less well at other things, because, you know, we don't have enough training data or we don't have the best architectures or learning algorithms, but they are a very powerful tool. So for the class goals, we're going to try to teach how to learn in detail about building NLP systems, particularly from a research perspective. Learn basic and advanced topics in machine learning and neural network approaches to NLP. Learn some basic linguistic knowledge useful in NLP, and learn methods to analyze linguistic structure. See several case studies of NLP applications and learn how to identify unique problems for each. We're going to introduce 4 NLP applications. These aren't the most important ones or the most the best ones ever or anything like this. It's just to give you some examples how we think about building NLP applications, and then you can apply those to other applications that you might be interested in. Another very important thing that I want to teach is learn how to debug when and where NLP systems fail and build improvements based on this. And this has been the key for a lot of my research career on how I have, you know, picked better directions and how to choose what to do next. And I think it's an important thing that I hope people can learn from the class too. So due to the Zoom mishap, I only have 4 minutes left. So I'm just going to go through the last part very quickly, and I can answer any questions at the end of class. But basically, we're going to talk about machine learning and neural network fundamentals. We're going to talk about sequence models, including recurrent networks, sequence labeling, condition generation, and attention. We're going to talk about representation learning and pre-training, including pre-training methods, multitask learning, prompting, interpreting, and debugging NLP models. For applications, we'll talk about machine reading and QA, dialogue, computational social science, bias and fairness, and information extraction and knowledge-based QA. For natural language analysis, we'll talk about word segmentation, morphology, syntactic parsing, and semantic parsing. And for advanced learning techniques, we'll talk about long sequence models, structured learning algorithms, latent variable models, and adversarial methods. And finally, a very quick thing about the class learning class format. It'll be in-person rotation, as you already know, so split into Tuesday and Thursday groups. On your day, you're encouraged to come in person. On the other day, you're encouraged to join synchronously. The class will be recorded for review. And the class content and format will be before class. For some classes, we'll have a recommended reading that we suggest you read before the class to get the most out of the class. And during class, we'll have the lecture and discussion going through the material. We'll sometimes look at code or data sets. And then after class, other than this class, which has no quiz, we'll generally have a quiz of some variety that you just fill in to make sure that you understood. It's not supposed to be really hard if you attend the class, just kind of a confirmation of your. The reference papers, no, those are basically things that you can click through to read if they sound interesting to you in class. There's like 30 reference papers for some classes, so if I asked you to read all of them, I would hope you would have not any other obligations for your entire weeks. Then finally, assignments. Assignment 1 is going to be build your own BERT. So basically what I'm going to ask you to do is to use PyTorch to learn about, use PyTorch to basically implement the weight reading and training of a pre-trained model BERT. If you're not very familiar with PyTorch, we'll try to have kind of a very quick getting up to speed thing for PyTorch. NLP tasks from scratch. Assignment 2, we're going to have teams, and you're going to be asked to solve an NLP task from scratch. And when I say from scratch, it means you're going to have to create data and train a model and set up evaluation. And this is meant to show you the whole life cycle of creating an NLP model. Like instead of just downloading a data set from Hugging Face or something like that, you're going to have to actually know what is in your data and figure out how to do annotation and stuff. I don't know exactly what the task is going to be. It might be analyzing research papers. but we're still trying to decide the final details of that. Assignment 3 is a state-of-the-art survey and re-implementation. So we're going to ask you to choose a task that you like and survey literature and re-implement and reproduce the results from a recently published NLP paper. Right now, we're collecting ideas from people who are familiar with NLP. You don't need to follow any of the ideas, but the ideas are things that we can suggest to you as like possibly good topics if you're not very familiar with NLP in the first place. Then the final project is to perform a unique project that either improves the state of the art or applies NLP models to a unique task. At the last classes, you're going to present a poster and then you'll write a report about it. All of these are team assignments, and you're going to do them in teams of 2 to 3 people, which means not 1 and not 4. And if you don't know anybody in the class, we're going to try to set up a thing where we have a very quick survey at the beginning of the class where you can fill in like what you're interested in, and we'll try to match you with people. But it wouldn't hurt to start, if you know people, it wouldn't hurt to start talking to people now and figure out who you want to work with. Yeah. So sorry, I couldn't hear the first part of it.
It's different from the website you can.
Oh, really? Okay. This is correct. It's possible that the website is old. I thought I updated it, but I'll take a look just to make sure. Yeah. Okay. Assignment 2 is definitely done in Teams. Is it the NLP system from scratch assignment, or is it the bird? Okay. Sorry, that's just a mistake, and I'll fix it. And then the instructors are me and Bob. And I'll be doing most of the lectures, but Bob will be doing the ones on natural language analysis. We have 10 wonderful TAs. I was planning on introducing them until my internet failed. So unfortunately, maybe we'll have to do that next time. But you can also look at what they're interested in on Piazza, because everybody's posted their interests. There's also office hours. We're still filling in the times of our office hours for all of the TAs, but the 2 instructors and all of the TAs should have office hours, so you can go discuss with them. Everybody is there to be your resource, so you can talk with people about anything you want, including project ideas, implementation things. That gives you an advantage, on the project, but that's what we're here for. We're here to give you an advantage, so please, take advantage of it. So that's all I have for today. Sorry for running over. I'll try to finish on time next time, but yeah, thanks a lot. Oh, wow, okay. Oh, sorry. So I'm totally not overtime, which means let's introduce the TAs actually. We have time to do that. I'm sorry, I messed up the ending time and thought it was 25. So we'll just go quickly through the TA introduction and then finish early. So our TAs are mostly over here. So if you could go in order from maybe the left side. Yeah.
Stand up, I think.
Yeah, stand up. Okay.
And the master students that here in the LTI and the MIS program. Yeah, I took this class last fall, and some of my interests are particularly in dialogue and natural language understanding. I also have a little bit of experience with linguistics.
Thank you very much, Ken. Everybody else, could you come in front of the camera so the people on Zoom can hear? Yeah, just for the people on Zoom, Ken is interested in like dialogue and linguistics and other stuff like that. So I won't repeat it, but yeah.
Hey everyone, is this the camera?
Yeah, and you'll need to talk loud because we don't have the mic.
Sure. Yeah, hey everyone, I'm Shubham and I'm in the second year of the MCDS program. So my interests lie in dialogue, particularly in dialogue evaluation, multilingual NLP, and natural language understanding.
Hi everyone, my name is Lucio Derry. I'm a 4th year PhD student in the CSD department. I work with Graham and I'm co-advised by Ami Talwaka in MLD. I'm interested in machine learning for NLP, so specifically transfer learning, multitasking, meta learning related stuff, and pre-training obviously. Cool.
Hey everyone, I am Aditya. I'm a second year master student in LTI. I'm doing my MIS degree. I am interested in question answering, dialogue, and like multilingual NLP in general.
cool. And if there's anyone on Zoom, any of the TAs on Zoom who could introduce yourself. I can't see the order, so if you could.
So let's go alphabetical. So Abhishek can start first, I guess.
Yeah,
Okay.
sure. Can you guys like see me too or just hear me?
You can see and hear.
Oh, okay. So hi everyone, my name is Abhishek. I'm a second year master's student as well, MIIS, and I'm interested in information retrieval, more specifically working on retrieval models that can generalize to new unseen domains. And I'm also interested in multilingual NLP. So if you want to work on code mixing or on low resource languages, and I'm also interested in controlled text generation and text rewriting, as well as parameter efficient models such as adapters for NLP. So yeah.
Thanks a lot.
Yeah, I guess I can go next. So hi everyone. I'm Kundan. I'm a PhD student in LTI. I'm remote right now, but I'll be with you soon, tomorrow. I work on text summarization. So I worked a lot on that, especially on like some human in the loop kind of learning for text summarization. Also more broadly, I'm also interested in like different ways for language modeling and text generation. And more recently, I've picked up a little bit of work on pre-training, kind of explaining why pre-training methods work and coming up with like slightly unusual, wacky ways of pre-training models. So yeah, it's been my work so far. I'm looking forward to like discussing ideas with you and advising you on your.
Great. Thanks a lot. So who are we missing? How?
Yeah, hi everyone, I'm Hao. I'm fourth year PhD student. My research interest is social intelligence.
How do you have a camera by any chance? If you can't, that's fine, but it'd be nice if we could see you.
No, it's sorry, I didn't
Okay.
prepare for it.
Okay, yeah, no worries.
Yeah, so I work on social intelligence embodiment for language learning and cognitive science. Really looking forward to seeing you.
If there's anyone else who can go, that'd be great. If not, then.
Oh yeah, I can also introduce myself. Yeah, so I'm Emmy. I unfortunately have COVID right now, so I probably won't be around until next week. But I'm interested in global interpretability methods and natural language understanding broadly. So if you're interested in that, we could definitely talk at some point. And I'm looking forward to seeing you guys next week.
Great, thanks. Bao, I saw you.
Yeah. Hi, everyone. I'm Bao. I'm a PhD student working with Graham, and I mostly work on knowledge-intensive tasks like question answering and slot filling. And I'm also interested in retrieval augmented models and prompting. So if you are interested in those topics, feel free to reach out, and I'm happy to help.
Okay, great. I don't know if there's anyone else. If there's no one else, then I just realized that Bob, you haven't like actually stood up and.
Bob as Graham said, I'm going to be. I'm Bob Friederkin. As Graham said, I'm going to be teaching the analysis parts of the course. Things like mechanisms that actually exist in languages independent of what technology you're using to understand them. That's probably
great. Okay. Okay, so thank you, everyone. I'm glad we had time to do that. Sorry, I totally thought the class ended at 25 past instead of 45 past, so I accelerated through the last part when it was totally unnecessary, but apologies. I'll have that down next time. So cool. See everyone later, and I'm happy to take any questions.